Okay, so we've looked at multi-layered networks, or at least we've talked about it briefly, where you have an input layer with possibly many inputs, many scalar inputs, lots of hidden layers potentially, and then an output layer with potentially many outputs. Um, and one can imagine making this deeper, in other words, many hidden layers, or wider, in other words, many neurons per layer. And the basic idea of approximating functions with neural networks is that by having a sufficiently wide network and or a sufficiently deep network uh, with lots and lots of neurons, and by appropriately changing the weights and biases, WI, we can essentially get arbitrarily complex functions. In fact, there is something called the universal approximation theorem for neural networks, which essentially say that if you have a bunch of inputs and a bunch of outputs, and you have a sufficiently complicated network, sufficiently complicated in the sense of being wide enough, specifically, and or deep enough, actually, in some cases, you can approximate arbitrarily complicated functions arbitrarily accurately by increasing the number of neurons in the network. Okay. Um, the theorem is actually relatively intuitive, at least for simple activation functions. But rather than see a proof of the theorem, let's actually build intuition by doing some MATLAB demos. Let me close that. Okay, so here's a MATLAB demo. Um, just to start with something really simple, imagine you have a single input x, which gets transformed into z here, which is w naught plus w1x, okay, where w naught and w1 are some numbers. Um, and then, of course, we can run this. We can plot x versus z. That's just a linear function, okay? And then you get y, which is z with the ReLU activation acted upon it, okay? The ReLU activation is just 0 when z is less than 0 and equal to z when z is greater than 0. So when you apply that, it will um, transform this thing into basically something that is 0 when z is negative and then positive when z is positive. So let me run that. Okay, so I just converted it into that. Um, so that's just y, which is ReLU of z, which is ReLU of w naught plus w1x. So that's a single neuron with a ReLU activation function. We can replace that with a different activation function, which is the threshold function or the binary step function. So instead of it being linear, it just looks like this. We can replace this with a sigmoid, where instead of this, we smoothly rise from 0 to 1. These are all different nonlinearities, and they have slightly different properties. Um, but essentially, we have a linear transformation plus a nonlinearity, right? So that's a single neuron. What we have done is a single neuron in an artificial neural network has this structure. And like we just saw, it's rather similar to what we did for logistic regression. Okay, so that's one input, one output. It would be called a single layer neural network with one input and one output, right? Let's now do a two-layer neural network, right? So what do we mean by a two-layer neural network? We have an input, and then we have a hidden layer, and then we have an output. The input layer is not considered an official layer of the neural network just because it is only an input and doesn't involve any transformations. And then the hidden layer does some transformations, a linear transformation and then a nonlinear transformation. And then the output layer also potentially does a linear and a nonlinear transformation. Um, so we'll talk about some details here, okay? Okay, so that's the structure we're going to do, and then we are going to make up some parameters and then plot the function that results from having these two layers, okay? So clear all, close all CLC. Okay, I'm just going to say num layers equals 2, not counting the input layer. We're just going to have a very simple function, single input, single output, okay? a single number comes in, a single number goes out. Okay, very simple. You can plot it x versus y. Okay, that's why. So we say number of inputs is 1. And then in layer number 1, which is the hidden layer, we're going to have 200 neurons. Okay, so the one input gets sent to 200 different neurons. Okay, and then the 200 different neurons do something to the one input, and then they all communicate their outputs to the one output neuron. And the one input neuron takes all of it, does some calculation, and then provides the one output. Okay, so that's the structure of the neural network. You can try to draw it out. Of course, each of these layers will have the bias term W naught, and then there will be as many bias terms as there are neurons in that layer. So that's why in layer number 1, the number of bias terms is num neurons layer 1, which is 200. Okay, there's going to be 200 bias terms, one for each neuron in that layer. And I'm just choosing them to be randomly generated between 0 and 1. Okay, and then weights, we're going to have basically num inputs times num neurons layer 1 weights. If there are more inputs, we'll have more weights, but in any case, it's now going to be a matrix with this and this as the sizes, rows and columns. And again, I'm going to choose it as rand, but in this case randn, just for better visualization, perhaps. Probably doesn't matter if I choose this to be rand as well. But I want them to be both positive and negative, so that's why I chose them to be randn. So that's for the first layer. And then the second layer, again, has a bunch of bias terms. In this case, it's just going to be one bias term because the second layer, the output layer, has just one neuron. And then potentially a number of weights. There's going to be weights corresponding to each of the edges that go from the second layer to the hidden layer to the output layer. So it's going to be a matrix of weights. Okay, so num layer 2 times layer 1 is going to be the matrix of weights. Okay, so we have all that. We just selected the weights and the biases to be random just for illustrative purposes. Okay, so we've now built, quote unquote, the network. We've completely defined the network, well, except for like what activation function and so on. But basically, we have all the parameters that we need to define the function. You know, the number of layers, number of neurons, the weights and biases. And this is all you need to evaluate the neural network function, of course, given what the activation function is and so on. Okay. Okay, so we've defined a function now. We are going to essentially evaluate this function for different values of input, x, and then compute the corresponding values of y, output, and then we're going to plot x versus y, right? So we're going to see, okay, the neural network is just a function. What does this function look like if you pick random weights, okay? We're actually defining the function rather than call a function. We're just defining the function literally here so that it's very transparent. In comes an x, so we are looping through different values of x here. And then in layer 1, we compute a z value, which is going to be bias, W naught, times weights, times input, right? W naught plus W1 times x, which is z. And then that gets acted upon by this nonlinearity. In this case, we're just using the activation, the step activation or the threshold activation function. So y is just this 0, 1 function of z. Okay, so that's going to be the output of the hidden layer. And there's going to be 200 outputs because the hidden layer has 200 neurons. And then those 200 outputs go to the second layer, namely the output layer, which again has the bias times plus weight times the outputs of the previous layer. And then we can potentially have the activation binary function as well. And then that's it. That's going to be your y layer, okay, output. Um, and then we can plot x versus y, okay. Let me plot these things. So let's plot this. It's actually probably not going to look very exciting here. And the reason why it's not going to look exciting is because um, in this layer, we are applying this activation function, which is just a binary, and the output now is just going to be 0 or 1, okay? Necessarily, because that's the final thing that we did to it. Okay, so it's 0 and then 1, and that's all that is. We can run this a few times. Potentially, it's now 0 everywhere in that range. Maybe we can increase the range a little bit